been quite a while since I've done a video, but here's one. So I picked up this oscilloscope, I did yesterday. Just wanted to fiddle around really, just to show what happens. An oscilloscope is basically a device that shows voltage as a deflection up and down. And what you can do, you can display it on the screen in varying speeds. So I wanted to show you a couple of things. So here's a PWM circuit that I built up, which runs at around about the same speed as a PC. It's not that far off. It's difficult to get it exact because it's, yeah, you know, it's just an analog circuit. I've got it connected up to one of my PWM converters. I haven't obviously chopped off the extra bit of board there yet. So I've got one scope probe. That's the yellow one, which is number 1, which is attached to the positive there. And on the other thing, other P&W, I've got the scope probe attached to the output. So basically it's going to be the same as what's coming in here into the circuit. Right, so at the moment I've got the potentiometer adjusted right up to the end, so this is roughly maximum duty cycle, and I can move it. What you see happening here, if I just put it on this one at the moment, so this is the PWM signal. The bottom of the screen there will be 0 volts, and the line that you're seeing is roughly 3.5 volts. So you've got 0 there, and because we've got it on 2 volts, 2, 3 and a bit. Okay, there's 1, 2, 3, 4, 5 graduations there, so you can work it out. 3 out of 5, you know, it's roughly 3.5 volts, and that's our signal then going into the circuit. If I bring on Y2, now this is the signal the fan is giving out on my circuit. So this is the signal the fan sees. Now this is also around 3.5 volts. Now this is a really low duty cycle. I'll show you again. That's around about, I don't know, 15-20%. You can see there's more down than there is up. So if I increase, I'll put that on. Now if I increase the duty cycle, I'll put both on, so we can see both. It may actually go out of triggering, but at the moment, as you can see, as I increase the duty cycle, the average voltage seen by the fan just keeps on increasing until we get to 1, 2, 3, 4, 5, near enough 12 volts. And obviously I can turn it down, put it back up. I think the reason it's juddering is because inside the fan there's inductors, and inductors like to hold on to energy, so they don't react that quickly to changes. So I'm trying to put let's put the second fan on. You see the voltage, just watch on the other scope there. So that's with one fan, and I'll put the second fan on in a moment. There you go, so you can see the difference. As I put it on, the voltage seen by both fans drops accordingly. Oh, one other thing I can show you, if I put the yellow one, the channel 1, which is the voltage that the fan is seeing, on AC, I can then, if I put it up at the middle of the screen, I can increase the wave, and you can see at 0.5 volt per division, you can see how much it's varying. I don't know quite this. It's a lot of variance there. I'm not sure what that is. I'm trying to see if I can get rid of that, but I can't seem to figure it out. One more thing, what I've done now, I've just added this 100 ohm resistor to my circuit. So this would basically draw at 12 volts. This would draw 120 milliamps. Rough calculation, it's probably more or less right. So this is how the scope looks with the resistor. Obviously it's a lot more steady because it isn't an inductive load on there. Same basic scale as before, 2 volts per division. As I increase the cycle, it goes up to 12 volts, 1, 2, 3, 4, 5, 6, yeah, 12 volts. With a tiny little pull down at the top there. and as I decrease the load, the cycle I mean, you can see that it drops all the way down there, and it'll go down to, well, half a volt. And I mean, it gets pretty hot. It gets pretty hot once you got it up 12 volts. This is probably a 1 watt resistor, and I'm putting over a watt through it at 12 volts, so that's going to get pretty toasty very quickly. But I thought that was cool. Just to show that it's not a fluke, this is a different one I put together a short time ago. And here we are on the scope again. There's the PWM cycle, down it goes. It goes. So what you've basically got is, I'll show you the little capacitor. Focusing really well. See that little capacitor there? Well, on the scope, I won't use a sharp end. On the scope you've got this point. This is when the cycle starts, charges the capacitor up a touch, and then when the PWM goes into off, capacitor starts to discharge. Because it's so fast, the capacitor can't react quick enough. As you can see, if I take it down there, it's gradually not getting a chance to charge up before it discharges again. So you probably find that capacitor to capacitor there'll be a difference in charging rate. Some will be faster, some will be slow, but of course then you can compensate for it with the potentiometer. If I was to use a low ASR capacitor, perhaps things would be different. Or if I used one of these metal films, things would be different because they're a lot faster. And these ceramic, if I used a ceramic cap on there, if I can make it big enough, you may find that this would look quite different. So I might build one up on some breadboard just to see what that looks like with different types of capacitor. Okay, so I've thrown the circuit together on breadboard. This is the form without a capacitor, which is interesting. You can see that basically there's a very acute angle there. I mean, our fall time is next to nothing at this kind of speed. You know, we're looking at microseconds, 4 or 5 microseconds. That's probably anyway, that's without capacitor. Very quick fall time. Obviously that energy's come from somewhere. It's probably coming from within the transistors themselves. There's obviously some capacitance in the circuit, and there's a little bit of capacitance and energy stored within. And this is the difference between no capacitor and a ceramic capacitor. You can see that it makes very little difference. Right, another one. I've got that's without a capacitor, and this is with a film capacitor. Now you can see that it falls, but it doesn't fall to zero, it falls near to zero. Now this particular capacitor is a 0.22 film capacitor, which is a hell of a lot smaller in capacity than that one. So I think I'll grab a 0.22 electrolytic. The difference between a 1 microfarad electrolytic and a 1 microfarad mylar film capacitor, which I pulled out of a microfilter for ADSL. So you can see there's very little difference between the two. These are the same rating, the same size capacitor, but the major difference I think is on the electrolytic, which I've got on now. You've got a a steep surge into the capacitor. With the Mylar, it's a little bit less pronounced, more steady. Now I'm going to try and put a large capacitor on, see what happens. Comparison in AC. So this is the standard capacitor, 22 microfarads. You can see that it's again drops down and gradually wears out. Drops down quite quickly and then smooths out. This is based on a resistor, of course. I'm just going to swap it over to a large cap, and you can see the difference. So we're going from far less. Doesn't rise as much because obviously the capacitor is bigger. Doesn't fill up as much, so you get less value out. That as I increase the potentiometer to the PWM converter, you can see that it tops out 12 volts faster and faster. So this explains why the fan curve was a little bit top heavy at times. If you adjust it too high, so as I bring it down there, perfect. That's where you'd want your fan curve. Perfect straight line. If you put it a bit too top heavy, then you'll find that it'll max out a little bit early. I suppose if I turned it all the way, then that would straighten that curve out.